Now it's time for chapter 21, podcast 4, which is determining redox reaction strength. So what we're going to do is we're going to look at our table that we saw at the end of podcast 3. We're going to look at that again and look at the trends in it and be able to figure out then, okay, right, we're going to look a little bit more in depth in what makes something a strong oxidizing agent or a strong reducing agent. So I've put the table of reduction potentials back into this podcast. It was in the previous one as well, so that you can easily refer to it whenever you need to, because we're going to use it quite a few times on this chapter. If you're given homework or you're given, something on an exam, you should have table of reduction potentials if you need them, right? As a reminder, all of these are reduction potentials. You can see that because all the things are being reduced. The electrons are always on the reactant side. Remember that oxidizing agents are shown on the reactant side as well, and they increase as we go up the table or become less and less negative or more and more positive. And on the product side, or on the right-hand side, we have our reducing agents, and they become stronger and stronger as we go down as our reduction potentials become more and more negative. And if we think about something like fluorine, if you look at where it is on the periodic table, it's in the upper right-hand corner, right? And it's a halogen. Fluorine really wants to get one more electron, right? The fluoride, to become the fluoride anion, it really wants to do that because then it's like a noble gas, right? And so as it gains an electron, right, it does that by oxidizing, right? Or oxidizing something else, making something else lose electron. Whereas the opposite is true for something like lithium. Way down on the right-hand side there, lithium, right? Lithium really wants to gain one more electron, right? Because if it does, it's going to look like a noble gas, right? The lithium cation looks like a noble gas. And so it really wants to gain an electron, meaning that it really wants to reduce somebody else. It really wants to steal an electron for somebody else. So it's a really good reducing agent. It's really strong. So we can see those trends in our reduction potential table by seeing that our reducing agent strength increases down the table. That should be in any book or any of our figures that we see, as long as, right, the reducing agent is going to increase as we go to our standard voltages being more and more negative, and our oxidizing agent strength increases up our table, right? Or whenever we have our reduction potentials increasing or becoming more and more positive, less and less negative, right? And the strongest reducing agent is lithium, and the strongest oxidizing agent is fluorine. Because lithium is such a strong reducing agent, right? Because it really wants to reduce things so much, it wants to react so badly, it can be very dangerous to work with. It reduces water to the point in which it reduces water, it gives off, it's an exothermic reaction, it reduces water into hydrogen gas and oxygen gas. Well, guess what? Hydrogen and oxygen, that's the makeup for a big old fire, right? Hydrogen is something that we can set on fire, especially whenever there is fuel for that fire, oxygen. Fluorine is a very strong oxidizing agent. It's also very dangerous to work with. Back in the 1960s, when they were first separating fluorine out on its own, right, just a single atom of fluorine, which doesn't happen naturally in the world around us. It's either fluorine, right, diatomic element, which is safe to be around, or fluoride ions, which is also safe. But when they were able to just separate out one single fluorine by itself, it was very dangerous. And in the 1960s, they were starting to do this, and there were several large explosions on university campuses. So luckily, we don't mess around with that stuff like that anymore. So hopefully we don't have one of those on our campus anytime soon. If we're interested in figuring out which species is a stronger reducing agent, right, which thing will reduce other things better than the other one, what we want to do is we want to look up the reduction potentials of each one of them in a table of reduction potentials, right? And then we can just compare those reduction potentials with each other, right? This is not a hard exercise here in sample problem 21-3, but it is, we just have to look them up in a table and then compare those reduction potential. So for part A, we're going to look at whether chromium or cadmium, CrCd, is a stronger reducing agent. All right, so I looked those up in a table of reduction potentials, and I've got chromium 3 plus 3 electrons is forming chromium solid. And the reduction potential for that is negative 0.744 volts. And then I did it also for cadmium. So I've got cadmium 2 plus 2 electrons is producing cadmium. And the reduction potential for that is negative 0.402 volts. Notice that we don't need these to have the same number of electrons in there or anything like that, right? It's independent. Those values are independent of the number of electrons. We found that out earlier in this chapter. So these don't have to equal each other or anything like that. All I had to do was look these reduction potentials up in their table as is, and then we're just going to see which one of them is more negative, right? And so the one that's more negative is for the chromium. So the chromium is a better reducing agent. That's all we have to do here. So let's go through these for iodide and bromide as well, and then hydroxide and our NO2 on the next slide as well. Continuing on with sample problem 21-3, we're going to do the same thing as we did in part A for part B, but instead we're going to look up the iodide anion and the bromide anion. We're going to look those up when they are products, right, or on the right side of our table, because we're looking for them to be, right, strong reducing agents, and those are on our product side. So I'm looking those two things up in a table, and I can find them where I get iodine plus 2 electrons forming 2 iodides, and bromine plus 2 electrons forming 2 bromides, and I can find the reduction potentials for both of those. Remember, we're wanting to find the one that's the most negative, or another way of saying that, we're trying to find the one that has the smallest positive value for the strongest reducing agent, and so the smaller of those two numbers happens to go along with iodide. We can do this one more time here for part C, where it wanted us to do hydroxide and then our nitrite anion. All right, so notice that in these two, on the top one, we have hydroxide. That was easy to find in the table. The harder one to find is the nitrite one, because notice that there is hydroxide in that as well. But what we're really reducing down in that, what we're really getting from that is NO3 down to NO2, right? That's what we're really reducing, right? Because if we think about everything in water, right? If I have the water molecule, each hydrogen in that water molecule is going to be +1. Oxygen is going to be -2. In the hydroxide here, right, the oxygen in that is -2. The hydrogen in that is +1. And so it's overall -1. And so nothing has been reduced in that. The only thing that's been reduced is going from our NO3, right, our nitrate, to our nitrite, our NO2. So again, now we're just going to look up which of these values is smaller. The reduction potential for the NO2, our nitrite, is 0.004. That's much smaller, so that is the correct answer. So this is just a quick picture of lithium as a reducing agent. Again, as I said, that lithium, right, is really good at reducing water, which is in our test tube shown on this slide. In that test tube, we got that little hunk of lithium that's in there. It is separating the lithium out, right? It's separating the water by reduction, right, into hydrogen gas and oxygen gas. This is a very exothermic reaction, which would set this thing on fire. In fact, if you did this, that entire test tube would eventually explode. Luckily, we caught it at just the very beginning of the fire there. They don't show a lot of that fire going on. That would explode very quickly. So in our next PowerPoint, which is going to be, or sorry, our next podcast, right, we are going to be calculating standard voltages by looking them up in our tables and using a couple of rules. But right, calculating them is basically adding two numbers together. So hopefully we'll be able to pull that one off. See you then.